I hope you have seen the chemical bonding part 1 revision video, which was already uploaded. It included the topics chemical bond, covalent bond, ionic bond, the properties of covalent ionic Lewis-Strauss structures, the limitations of octet rule, and bond parameters like bond angles, bond length, etc. So I think you have revised. So on to the second part, and the topics we are going to cover here will be resonance and dipole moment. So let us proceed. Watch this carefully, and I am repeating that these revision videos will be helpful for your unit exams, your term tests, as well as for NEET and JEE. So these are going to give you all the basics required for your basic preparation, understanding of the topics, and these videos are in the order of sequence of NCERT topics. So stay tuned, listen carefully, and let us proceed. So the next topic we are going to deal with is resonance structures. What is resonance and what is the need for resonance? According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy, position of the nucleus, bonding and non-bonding electrons are taken as canonical structures of the hybrid, which describe the molecule accurately. So if I give you the simplest possible example here and tell you that if I have to draw the structure of benzene, the structure of benzene is drawn like this. So if I label the carbons with numbers, then I understand C1 and C2. This bond is a double bond, and it should have a smaller bond length in comparison to the C2 and C3 bond, which is expected to be a single bond and hence is expected to have a longer bond length, 154 picometer. We know, we checked in the last video, bond order is directly proportional to bond strength, but inversely proportional to bond length. More is the bond order, lesser is the bond length. But in reality, experimentally, what has been observed, each of the CC bonds, each, this one, as well as this, as well as this, as well as this, was found to be somewhere in between that of a single and a double bond, suggesting that this structure is not depictive of the actual properties of benzene molecule. So there are so many such problems. If I look for, let us say, a carbonate ion, we learned in the previous video how to draw the Lewis-Strauss structure and understand the bond parameters of carbonate ion. This is a structure of carbonate ion according to which this C double bond O should have bond order 2, and both this and this should have bond order 1. But in reality, it is observed each CO bond is found to have a bond order between 1 and 2, that is 1.33. So this observation could not be explained if we draw just one structure of carbonate ion. Hence, the concept of resonance was proposed. So what is resonance? Basically, it's a phenomenon of drawing some hypothetical structures, more than one structure, so that all those structures together can explain to us the properties of the compound, right? And none of the individual structures is able to explain all the properties. So let us see further. Let us say we have the Lewis-Strauss structure of ozone, and we discussed in the last class how to draw this in the last video. So this is a Lewis-Strauss structure of ozone, and this is also the Lewis-Strauss structure of ozone. How did we get from here to here? We simply took this electron, this one electron pair, we took it here and shared between these two oxygens, and in turn, one electron pair we shifted here. As a result of which, what happened? This became a single bond, and this single became a double bond. And since this is getting one pair of electrons, it gets a negative charge. We can even check this by trying to find out the formal charge. The formal charge on this oxygen should be 6 valence electrons minus 4 unshared electrons, that is 2 lone pairs means 4 electrons minus half of 2 bonds, that means 4 electrons. So the formal charge here should come out to be 0. Whereas if I calculate the formal charge here, it should be 6 minus, there are 6 non-bonded electrons minus half of 2 because there's only one bond. So we get the answer as -1, right? Originally ozone means we have 3 atoms. So the structure could be this, or the structure could be a single bond here and a double bond this side. So what are these two structures called as? These two structures are called as resonating structures. And to make one from another, what did we do? We simply moved the electrons. So these are the two resonating structures for ozone. These are also called as canonical forms or contributing forms. Resonating structures, canonical forms or contributing forms, any of the names can be given to these structures. So in reality, this shows what is the bond order of each OO bond. Because one bond is double, other is single. So actually it was found each bond is having bond order of 1.5, which could not be explained by one single structure, but we could justify it by drawing two structures where in one structure this is double and this is single. Hence the average of these two comes out to be each bond being 1.5. So this structure is called the resonance hybrid. How do we draw the resonance hybrid? Resonance hybrid is the net outcome of the various resonating structures. Like in this case, if I look at this bond, this OO bond, it's double here and single here. So I make 1.5 bond here. Similarly, it's double here and single here and double here. I make 1.5 bond. And similarly, we can distribute the charges. The total charge on this in both structures is +1, and this is delta minus and delta minus, which means minus is distributed over these two oxygens. Clear? And also, we could calculate the bond order by using a formula, the total number of bonds between two atoms in all the resonating structures divided by the number of resonating structures. For example, in case of ozone, if I just look at this bond, I can see here there are 2 bonds, here there's 1 bond, so total bonds between these two atoms are 3. 1 plus 2, 3, and this is in two resonating structures, so the bond order comes out to be 1.5, right? So now let us check the stability of the various resonating structures. The resonance hybrid, that is the overall outcome, is considered to be the most stable form. This is just the experimental structure, the real structure, right? And the resonating structures are the theoretical structures. And the resonance hybrid is more stable and has less energy, whereas the resonating forms have more energy and they are less stable. But together, they help in describing the overall properties of a molecule, which one single structure cannot justify. Right? Okay. The loss of energy is called resonance energy. What is resonance energy? Resonance energy is basically the difference in energy of the most stable contributing form contributing structure minus energy of the resonance hybrid. Right? So This is how we calculate resonance energy, but this is not given in NCERT. So if you want, you can leave it for the school exams. So what else do we understand? If we look at OO single bond, it should be 148 picometer. O double bond O is 121. But in ozone molecule, each bond has been found to be of 127 picometer. That means this bond is in between that of a single and a double bond, which can only be explained by taking the concept of resonance, right? So what more do we need to know about resonance? Resonance stabilizes the molecule as energy of the resonance hybrid is less than the energy of any single canonical structure, which means the resonance hybrid is also the most stable form out of all. Resonance averages the bond characteristics as a whole. What do we mean by this? It averages the bond characteristics, like this bond was double and this was single. And in this case, this was single and this was double. So in reality, each OO bond is in between that of a single and a double bond. So thus energy of ozone resonance hybrid is lower than either of the two canonical forms. And resonance hybrid is shown by a triple-headed arrow, resonating structures by a double-headed arrow. And these structures are the hypothetical structures, whereas resonance hybrid is the real structure. This is the real experimental molecule. But this does not have a well-defined molecular structure. It can be explained only by drawing these two different structures. Okay, now the canonical forms have no real existence. The resonance hybrid is the real molecule. And these facts are not correct. The molecule does not exist for a certain fraction of time in one form and other fractions of time in another canonical forms. There is nothing like equilibrium. Neither are these two resonating forms isomers of each other. They are neither in equilibrium nor are they isomeric forms. These are simply hypothetical structures drawn to explain this real structure whose bond length is in between that of a single and double bond. Bond order is also in between that of a single and double bond. Okay, so I give a very interesting example when I teach resonance. It's just like imagining a gambling table, the gambling table that you find in casinos. Okay, if you see carefully, there are different colored strips here. Different colored strips like red, violet, indigo, blue, green, yellow, and so on. And when this is turned at high speed, what color do you observe? You observe the white color. So white is the real experimental molecule that you're observing. But can you store that whiteness? No, because the moment this table becomes static, you start observing each of the individual colors, right? So actually this whiteness is made up of all these different colors. So what are these different colors? These different colors can be considered as the resonating structures. And this whiteness is the resonance hybrid. But this whiteness cannot be explained theoretically unless we take a combination of all these. So somewhat this kind is the concept of resonance. Okay, for every molecule, we draw hypothetical structures to explain a situation which is not explainable by a single structure. Okay. Now, what are the examples of resonance? Let us suppose we were to draw carbonate ion. How am I going to draw the resonating structures of carbonate? We cannot change the skeleton of the molecules in resonance. When we draw resonating structures, we have to keep the skeleton the same. So these are the three resonating structures of carbon. That means position of atoms is the same. Position of atoms in each of these structures is O, O, and O. We cannot change the position of atoms. What we can change is the pi electrons, the second bond, and the unshared pair of electrons. How do we do that? If I want to make the resonating structure, what I do, I bring this one electron pair here. This electron pair, I force it to be shared between this O and this C. In turn, this bond I convert to a lone pair. So I'll be getting this structure because this one extra bond has been forced to come here, this one, and this one extra pair from here has been converted to a double bond. So I get the next structure. Now here what do? I let this come here and this go here. I get this structure. Fine. These are the three resonating forms. Now supposing I want to find out the bond order of this bond 1. So CO bond 1, how do I calculate? The bond order, we discussed a formula, is calculated by the total number of bonds between one pair of atoms, say carbon and oxygen. So 1, 2, 3, and 4. There are 4 bonds and there are 3 total structures. I divide it by 3, I get it as 1.33. Or if I want to explain it logically, then this position has one bond in all the 3 structures. There's a single bond in all the 3 structures, means bond order is 1. Plus this second bond is divided into 3 positions. Either it's here, or it's here, or it's here. One bond is divided between 3 places. So what is the contribution of this towards each structure? 1 by 3. So the bond order of each CO bond becomes 1 by 3, that is 1.33. I hope this is clear, right? I repeat, either you calculate bond order by the formula or divide this one double bond over 3 positions, because each position is having definitely one single bond in each of the 3 structures. The single bond is there in each of the 3 structures. So each bond is going to have bond order 1. Plus this multiple bond, second bond is divided over 3 positions. So towards each its contribution is 1 by 3. Hence the bond order is 1.33. So that's how we draw the bond orders. So what is the formal charge on each oxygen? This 2 negative charge is divided over 3 oxygens, because in reality either this and this is -1, or this and this is -1, or this and this is -1. So basically a 2 negative charge is distributed over all the 3 oxygens. So the formal charge on each oxygen in the resonance hybrid is equal to -2 by 3, as written here, -2 by 3. And what is the bond order? 1.33. Similarly, we've drawn here nitric acid. So the resonating structures of nitric acid will be shown like this. How do I help to make this? I just take this here and shift this here, as a result of which this bond will get converted to this electron pair and hence gets a negative charge. Negative charge can be calculated using the formula of formal charge, and this pair has shifted here, so I get a double bond here. Clear? So these are the 2 resonating structures for nitric acid. Similarly, you can be asked any of these for school exam. Ozone is very important. So we move on to the next topic, that is polarity of bonds. What is polarity? No bond in a compound is either completely covalent or ionic. Just to remind you, covalent bonds are those which are formed by mutual sharing of 1, 2, or 3 electrons. For example, this is a single covalent bond, this is a double covalent bond, and this is a triple covalent bond. An ionic bond is formed by complete transference of electrons from one to another. This is always between dissimilar elements and requires a difference of electronegativity. But covalent can be formed between similar or dissimilar atoms. Fine. An ionic compound means there's a complete separation into charges, but a covalent compound is either having no charge separation or partial charge separation. What is the meaning of partial charge separation? Like in this H and this Cl. One is more electronegative. That means if we talk in terms of emotions, electronegative means more greedy. So more greedy means this would want to keep the shared electron pair a little more towards its end. Why? Because the more greedy atom, more electronegative atom, right? So when it keeps a shared pair more towards itself, it tends to get some negative charge. When do we use delta negative? Delta negative means less than a complete negative charge. And this is delta positive. If there's a complete charge, one unit charge plus one and minus one, unit charge has value 1.6 into 10 to the power minus 19 coulomb. Now, if sodium chloride has 1 plus and minus 1 charge, that means the value of this charge is plus this much, and value of this charge minus 1 means the value of this charge is minus 1.6 into 10 to the power minus 19 coulomb. We call these as a unit positive and a unit negative charge. But a partial charge, delta plus, means a charge less than minus or plus 1.6 into 10 to the power minus 19 coulomb charge. This is partial charge. Partial charge is observed in polar covalent bonds, and complete charge is observed in ionic compounds. Okay, partial charge means less than complete because it's not formed by complete transference but simply by uh, shifting of the electrons more towards the greedy or the more electronegative atom. So when covalent bond is formed between two similar atoms, for example, these hydrogen, oxygen, etc., the shared pair of electrons is equally attracted between two identical bonds, which means if I'm writing hydrogen, then the shared pair is going to be exactly in the center of the two. But if I'm talking about HCl, the shared pair is towards the more electronegative atom. And wherever electrons are more, that part tends to get some extra charge. So these are called non-polar and these are called polar. Polar because two poles, oppositely charged poles, the positive and the negative poles have been created. Hence we call it a polar covalent compound. And in case of heteronuclear molecules, I've already explained this point to you. Now, as a result of polarization means charge separation, as we have talked of in HCl molecule. The molecule possesses some dipole moment, which is defined as the product of charge on any one of the poles and the distance between the poles. Or in other words, we say mu is equal to Q into D. The formula goes as mu is equal to Q into D. This charge is Q and this distance is D. Now, the quantitative measure of polarity. What is dipole moment? Quantitative measure of polarity is dipole moment. It is expressed as mu. It is equal to E into D or Q into D, where Q is the charge and D is the distance of separation. Dipole moment is usually expressed in debye units, capital D, where one debye is these many coulombs meter. So basically the unit is charge into distance. So the unit will be charge unit is coulomb, distance is meter. So it's either coulomb meter because this is the SI unit of charge and meter is the SI unit of length or distance. And ESU is the CGS unit of charge and centimeter is the CGS unit of length. So it's either these many coulomb meter or these many ESU centimeter. Dipole moment is a vector quantity, is denoted by a small arrow with tail on the positive center of positive center and head pointing towards the negative center. What does it mean? Supposing I want to express the dipole moment of this molecule, which is a polar molecule, I'll start an arrow from hydrogen pointing towards chlorine. This has to be the tail and this is the head. So the tail starts from the electropositive atom and it points towards the electronegative atom. Similarly, let us suppose I was to talk of carbon dioxide molecule. I would have shown the dipole orienting from the electropositive to the electronegative part. So since it's a vector quantity, the directions to which these dipoles are oriented is going to be very important. So dipole moment in polyatomic molecules, in case of polyatomic molecules, the dipole moment of individual dipole moment not only depends upon individual dipole moments of bonds, which are known as bond dipoles, but also on the spatial arrangement. For example, if I talk of a carbon dioxide molecule, let us say I'm talking about water molecule. Now, is water molecule a polar molecule? How do we decide? Water has two polar bonds. This is partial plus, partial minus, and partial plus. So if I have to draw the dipoles, this is going to get oriented in this direction, this in this direction, and then water also has two lone pairs. The dipole moment due to the lone pairs is oriented outwards because electrons are more negative, so the dipole is always expressed outwards. Here it's from electropositive to electronegative. And since it's a vector quantity, if we see the net effect of these three dipoles, it is all getting added in the same direction. So mu for water is not equal to 0. Water is a polar molecule. Water is a polar molecule having polar bonds. Now, if I look at BF3 molecule, what happens in BF3? The structure of BF3 is like this, right? So this is the direction of these two dipoles. And if I find out a vector sum of these dipoles, in which direction will be the vector sum of these? It will go in this direction. And this vector sum is going to cancel off with this third dipole. Hence, the total dipole moment comes out to be 0. Mu is going to be 0 for BF3 molecule. Why? Because the dipoles ultimately will cancel off. I repeat, this and this are going to have their vector sum in this direction, which is going to cancel off this dipole in the opposite direction. So the net dipole is going to be 0, and this is a symmetrical molecule with no lone pairs. Similarly, if we look at carbon dioxide, the dipoles in the two opposite directions. This is one dipole from carbon to oxygen, another from carbon to oxygen, equal magnitude and 180-degree angle. They completely cancel off each other. The net dipole moment comes out to be 0. So mu is again 0. So what can I say? What can I describe? I can say in carbon dioxide, the net dipole moment is 0. Net dipole moment is 0 in carbon dioxide. But so carbon dioxide is a non-polar molecule. What would I say? Carbon dioxide is a non-polar molecule, but it has polar bonds. So in spite of having polar bonds, why is it non-polar? Because the dipoles cancel off each other. We're just talking of the NCERT limits. Similarly, here's the comparison of ammonia and NF3. See, this is ammonia. How do we orient the dipoles in this case? The dipoles are oriented like this because N is more electronegative. So from H to N we will show. This is the lone pair goes outside. Overall, all the dipoles show additive effect. They add up. But if I'm talking about NF3, similar structure, but if I draw the dipoles, this time they're going to go in this direction. Why? Because out of N and H, N is electronegative, more electronegative, but out of N and F is more electronegative. So the direction of dipoles is going to be opposite, but this goes outward. So what will happen here? Here the directions are opposite. This is going to be cancelled by the net vector of the other three. These three net vector is going to come out in this direction. It's going to cancel off this. So this is a subtractive effort. So which is more polar? Ammonia is going to be more polar than NF3. Why? Because here all the dipoles are going to get added up in this direction, but here there's an opposing effect. So NH3 is more polar than NF3. This is one of the important questions. You don't have to remember the actual values of these. Actual values are not required. You just need to understand ammonia is more polar than NF3 and why. This point I've already explained. So which of the following molecules will have a zero dipole moment? How are we going to check this? Carbon dioxide, zero dipole moment. So I've shown you the answer. Why is it so? This is carbon dioxide. The dipoles are going to cancel off. Carbon tetrachloride. Again, the dipoles are going to cancel off. Why? Same magnitude. Symmetrical molecule, they all cancel off. BF3, they again cancel off. Symmetrical. BEF2, these are also going to cancel off. How are they going to cancel off? Simply like carbon dioxide. It's opposite directions. So all these molecules are going to have mu zero. So if we talk of NH3, let us say we're talking about NH3. NH3 structure has 3 bond pairs and 1 lone pair. And as you can see, the dipoles are not going to cancel off, but add together. So mu here is not equal to 0. Right? Similarly, chloroform. Although that's a tetrahedral arrangement, the magnitude of all these is not the same. So dipole moment is not 0. Similarly, water. Water also has bond pairs and lone pairs. So the net dipole moment adds up. Again, it is non-zero. So the green ones are polar molecules because they have some dipole moment, whereas the red ones are non-polar molecules. Non-polar means having dipole moment 0. Write the decreasing order of dipole moment amongst these compounds. You have to memorize this is the order of dipole moment, and this cannot be theoretically predicted as such. It is based on cancellations and checking the values. So CH3Cl is more polar than dichloromethane, more than chloroform. So pick up the answer, which is a polar covalent molecule. You understand it is HCl, polar covalent, because the first three are made between similar kinds of atoms. Which is a correct statement? So we've just discussed this example. The right answer is D part. Now next we have Fajan's rule. Fajan's rule basically will help us to find out percentage of covalent character in an ionic bond. Okay, and no bond is 100% ionic or covalent. Uh, some years back, it was considered that non-polar covalent bonds such as hydrogen, chlorine, etc., should be non-polar and should be perfectly covalent. There should be no charge separation. But since a few years, the concept is none of the bonds is 100% ionic or covalent because it is believed every atom has a capacity to affect the electron cloud of another atom. Okay, so to predict the nature of bond form, Fajan introduced some empirical rules to determine the percentage of ionic or covalent characters. So what did he say? He suggested the rules based on smaller cation. See, smaller is the size of anion and larger the cation, more is the ionic nature of bond, or vice versa. If you do vice versa, then smaller the cation, larger the anion, more is the covalent nature. Okay. So, for example, if I compare these ions, iodide is the largest size anion. Cations are same. Largest anion means sodium iodide is most covalent. And this is the order of ionic nature. Okay. And the second point says high charge on both cations as well as anions correspond to more covalent character. For example, if I ask you sodium chloride or magnesium oxide, which is more covalent. So, how are you going to decide? In this case, the charges are +1, -1. Here it's more +2, -2. So, higher the charge on cation and anion, more is the percentage of covalent character. So, magnesium oxide is more covalent than sodium chloride. Fine. Similarly, if I had asked you, let us say, sodium chloride and sodium bromide. This time the cation is the same. Larger anion means more percentage of covalent nature. Okay. And supposing the cation was different, that means I compared between KCl and NaCl. This time anion is same. So we know smaller cation means more covalent. So here the point is small cation, sodium ion more covalent. Here large anion, bromide ion is more covalent. And here high charge on both cation and anion is more covalent character. Okay, so if I'd asked you which is more covalent, SnO2 or SnO, how would you decide? You will check the oxidation states. The oxidation state here is +2, this is +4. So high charge is going to be more covalent character. This is Fajan's rule. Now, cations with noble gas configuration cations with inert gas configuration form compounds with more ionic character, and cations with pseudo noble gas configuration show more percentage of covalent character. Now, what is pseudo noble gas and noble gas configuration? If I talk of sodium, the configuration is 281. Or if I write down the modern configuration, it's 1s2, 2s2, 2p6, and 3s1. And for sodium ion, one electron removed means 1s2, 2s2, 2p6. That means 8 electrons in the valence shell. Right? This is noble gas configuration. Noble gas configuration. But if I look at pseudo noble gas and I pick up copper, the outermost configuration, the complete configuration, Z is 29. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d10. So what will be the configuration of copper 1 plus ion? You know, when we make ions, electrons have to be first removed from the highest principal quantum number. So the s electron, 4s1, will be lost. Copper ion is this, which means this is the valence shell and it has 18 electrons. This is called pseudo noble gas configuration. Pseudo noble gas configurations account for smaller size. Why? Because ineffective screening of intervening d electrons makes the Z effective higher and size smaller. Okay. Hence, we say copper chloride will be having more covalent character than sodium chloride. Noble gas configurations account for more ionic nature. Pseudo noble gas account for more covalent nature. Right? Now, pick up this answer. You can pause, think, and then pick. Covalent character is most favored for small cation, large anion. Ionic nature of the bond is lowest in. Give a thought. Ionic bond lowest means most covalent. For most covalent, what do we look for? Small cation. Here the cation is common. So you're going to compare the anion. Larger anion is more covalent and least ionic. Ionic nature is more in, again, how are you going to think of? AgF. Why? Smallest anion means most ionic. Compound with more covalent character. How are you going to think here? So more covalent out of the first two should be this. Out of these two should be this. And how are we going to compare these? This is the pseudo noble gas configuration. And this is going to be noble gas. Calcium ion is noble gas configuration and zinc ion is pseudo noble gas configuration. Fine. So that's how it goes. Now this time anion is same, cation is different, and a smaller cation is more covalent. So larger cation is most ionic. This time cation is same. So smaller anion is more ionic and larger anion is most covalent. I hope the concepts still here are clear. I hope this helps you children in your preparation for the exams. And if you like it, please share, subscribe. And in case you have any comments, you want the next videos to be differently explained, more brief or more detailed or more question bank, please feel free to share. Thank you. Have a great day and all the best for your coming exams. Study well.